This is Solved Problems in Microwave Engineering Part 2. A tutorial material from Tutors for students in science and engineering technology programs at intermediate, undergraduate and undergraduate levels. Authored by Tunde Emmanuel. An online tutorial class on YouTube by Tutors. So, question 1. A transmission system using a T10 mode waveguide of dimensions A 5 cm, B 3 cm is operating at 10 GHz. Now, the distance measured between two minimum power points is 1 mm on a slotted line. Now, calculate the VSWR of the system. In this aspect, we are dealing with waveguide, rectangular waveguide. And in the question, it has been given that the frequency is 10 GHz with dimensions of A 5 cm, B 3 cm. For a T10 mode, we have the waveguide. The wavelength of the guided wavelength is given to be lambda naught, which is the wavelength at this free space, all over the square root of 1 minus the square of the fraction of lambda naught over lambda c. That is the cutoff wavelength. Now, this formula is what we can use to calculate the guided wavelength. But as it is given in T10 mode waveguide, your cutoff frequency is 2 times A. That is the longer part of the rectangular wave. 2 times, and A dimension A is 5 cm. So you have 2 times 5, which is 10 cm. Then for you to calculate the lambda naught, which is the wavelength at the free space, you have the velocity over frequency, which gives 3 times 10 raised to the power 10 all over 10 times 10 raised to the power 9. All gives you 3 cm. Then we were also given the distance between the two minimum power points, which is 1 mm, which is equivalent to 10 raised to the power minus 1 cm. So if we substitute into this the waveguide wavelength, we have 3 all over square root of 1 minus the square of the fraction of 3 over 10, and that gives us 3.144 centimeter. So for us to now calculate the VSWR in this aspect with this method, by using the double minimum process method, it gives us the lambda g, which is the guided wavelength, all over pi into bracket d2 minus d1. So by the time we substitute our calculated values of the waveguide, we have 3.144 all over pi into 1 times 10 raised to the power minus 1. Therefore, the VSWR gives us 10. Now, question 2. Define velocity modulation. The B part says, what do you mean by klystron? And the C part, mention the application of two-cavity klystron. D, define transit time in reflex klystron. Solution to A. Velocity modulation is the modification of the velocity of a stream of electrons by impacting alternate accelerations and decelerations to the electrons so as to effect bunching. This bunching results in cycle of current as it passes through the output electrodes. Now, the B part. A klystron is a vacuum tube that can be used either as a microwave generator or as an amplifier of power at microwave frequencies, which is operated by the principles of velocity and current modulation. Now, the C part of the question says, what are the applications of two-cavity klystron? Now, number one, two-cavity klystron can be used in troposphere scatter transmitters. 2, it can be used in satellite communication to ground stations. 3, it can also be used in UHF TV transmitters. And 4, it can be used as radar transmitters. So, the D part, asking us to define transit time in reflex klystron. The time taken by the electron to travel into the repeller space, because in reflex klystron there is repeller space and there is bunching space, there is drift space. We have the bunching, we have the buncher, we have the repeller. Now the time taken by the electron to travel into the repeller space and back to the gap in the electron tube in a reflex klystron is called transit time. Okay? Question 3. A. Write a short note on number 1, the O-type tubes, and 2, the M-type tubes. What is meant by microwave resonators? The C part says, describe the tunneling phenomenon. And the D part, what are the applications of tunnel diode? In this question, for aspect A, which gives us that we should differentiate and talk about the O-type tubes and the M-type tubes. The O-type tubes, the O-type tube klystrons and traveling wave tubes are linear beam tubes in which the accelerating electric field is in the same direction as the static magnetic field used to focus the electron beam. Here, the electron beam travel in a straight line. And in another way, we have the M-type tubes. Now, magnetrons are crossed field devices where the static magnetic field is perpendicular to the electric field. In this tube, the electron beam travel in a curved path. So you can see the difference between the O-type tubes and the M-type tubes. The B part, for us to talk about microwave resonators. Microwave resonators are tunable circuits used in microwave oscillators, amplifiers, wave meters, and filters. So, at the tuned frequency, the circuit resonates where the average energies stored in the electric field and the magnetic field are equal, and the circuit impedance are purely real. Now, the C part of the question says, describe tunneling phenomenon. Now, when the doping level is increased, the depletion region reduces. Due to this depletion region, even for a very small forward bias voltage, Many carriers penetrate through the junction and appear at the other side. Now, this phenomenon of penetration of carriers through the depletion region is known as tunneling. So the deep part, what are the applications of tunnel diode? Number one, it can be used in relaxation oscillator. Two, it can be used in microwave oscillator. Three, storage device. And four, as pulse generator. And number five, high-speed switching networks. So these are the applications of tunnel diodes. Question 4. What is an ideal directional coupler? And the B part says, what are the uses and properties of an ideal directional coupler? So, solution to A. A directional coupler is a passive RF device that is used to sample a small amount of microwave signal for measurement purposes. At the same time, a directional coupler is a passive RF and microwave device which couples part of the transmission power by a known amount through another port, often by using two transmission lines set close enough together such that enough passing through one is coupled to the other. The device has 4 ports. We have the input transmitted port, the coupled port, and isolated port. The term main line or the primary main waveguide refers to the section between ports 1 and 2, while the secondary auxiliary waveguide refers to the section between the ports 3 and 4. As you can see in the diagram, we have the waveguide where we have the primary waveguide feeding port 1 and port 2, and the secondary waveguide where we have port 3 and port 4. So this is a sample of the signal flow in a directional coupler. So port 1 is the input port, port 2 is the transmitted or the output port, and port 3 is the coupled port, where port 4 is the isolated port. Okay, question 5 now. The A part says a line has a phase constant of 29.8 rad per meter at 1000 megahertz. The wavelength is watts. Now the B part says explain the principle of operation of klystron. Okay. Solution to A. In a transmission line, the wavelength and the phase constant are related by the equation lambda equals to 2 pi over beta, where beta has been given to be 29.8 rad per meter. Therefore, by substituting our values into this equation, we have 2 pi over 29.8, which gives 0.211 meter. Therefore, at 1000 megahertz, the wavelength is 0.211 meter. Now the B part, explain the principle of operation of klystron. A klystron is a vacuum tube used for generation and amplification of microwaves. As you can see in the diagram, an electron beam is electron beam is produced by oxide-coated, indirectly heated cathode and is focused and accelerated by focusing electrodes. These are the focusing electrodes. This beam is transmitted through a glass tube. You can see it is made of glass. It's a glass tube. Now, the input cavity where the beam enters the glass tube is called the buncher. You can see the buncher cavity. The buncher cavity. As electrons move ahead, they see an accelerating field for half a cycle and retarding field for the other half cycle. You can see all these things happen within the drift space. Therefore, some electrons now are accelerated and some are retarded. This process is called velocity modulation. And at the long run, this velocity modulation also impacted current density. So the velocity modulation causes bunching of electrons. This bunching effect converts velocity modulation into density modulation of beam. Now, the input is fed at the buncher cavity and the output is taken out at the catcher cavity. This is the catcher cavity and this is the buncher cavity, between which we have the drift space where acceleration and deceleration of electron movements take place. So you can see the grounding on the, and we have the cathode. We have the cathode, and we have the catcher cavity made of where the output signal goes out. The input signal comes in through the buncher cavity and the signal goes out through the catcher cavity. So this is the sample of the diagram. Question 6. The A part, what are the characteristics of a lossless line? And the B part, what is the transmission coefficient of a transmission line with Z0 300 ohm and ZL 300 minus J300 ohm? Solution to A. A lossless line is a transmission line with no resistive or direct dielectric loss. Number 1, it does not dissipate any power or any power loss because the resistive load, the resistance is always 0. There is no resistance, there is no dielectric loss. So it doesn't dissipate any power loss. Like I square R will give you 0. Number 2, it is non-dispersive, where the phase constant varies linearly with frequency. Number 3, its characteristics impedance, which is Z0, is real. Number 4, a lossless line is defined as a transmission line that has no line resistance and no dielectric loss, which means both the conductor and the dielectric are perfect in such a way that the conductivity of the conductor is infinity while the conductivity of the dielectric is 0. In this aspect, the resistive load is 0 and the conductance is 0. Number 5, for a lossless line, the attenuation constant is 0, but the phase constant is non-zero. Hence, from this equation, gamma equals to alpha plus j beta, where gamma is the propagation constant, the alpha is the attenuation constant, and beta is the phase constant. We have gamma equals to j beta because as it is given that the attenuation constant is always 0, so it is imaginary. The propagation constant is imaginary as related to LC circuit. We have j omega square root of LC. That means the propagation constant is an imaginary function. Number 6, the speed of wave propagation is the same as different frequencies travel across it. Number 7, when a transmission line is terminated with its characteristics impedance, Z0, all energy will be transferred to the load and no energy will be reflected. Therefore, the reflection coefficient of a transmission, of a lossless transmission line is 0. Number 8, in a lossless line, the electric fields are produced by voltage, while magnetic fields are produced by current. Now, the B part of the question says we have Z0 to be 300 ohm and the load impedance to be 300 minus J 300 ohm. Now, we want to calculate the transmission coefficient. Transmission coefficient is 1 plus the reflection coefficient. That's the reflection constant. Now we have the reflection coefficient to be ZL minus Z0 all over Z0 plus, that's ZL plus Z0. So given that, if we had it 1 plus the reflection coefficient gives us 2ZL all over ZL plus Z0. By substituting the values of Z0 and ZL, we have 1 minus J all over 1 minus J 0.5. And by following the principles of rationalization, we are able to get 1.2 minus J 0.4, which is equivalent to A minus JB. So we can now find our modulus R to be the square root of 1.2 square plus 0.4 square, which gives us 1.265. Now the angle of inclination is, which is theta, is calculated to be arc tan 0.4 all over 1.2. That gives us minus 18.43. Therefore, the transmission coefficient of the transmission line is 1.265 with inclination angle of minus 18.43 degree. Question 7. A line has Z0 of 300 ohm if the ZL is 150 ohm. Now calculate the reflection coefficient. And the B part says a lossless line of characteristics impedance is terminated in pure reactance of minus JZ0. Now, what is the VSWR? And the C part, what is impedance matching? The solution to A, given that Z0, which is the characteristics impedance, is 300 ohm, the load impedance to be 150 ohm. We have reflection coefficient to be ZL minus Z naught over ZL plus Z naught. So if we substitute the values given in the question, we have 150 minus 300 all over 150 plus 300, which eventually gives us minus 0.3. Therefore, in a lossless line where the resistive load is less than the characteristics impedance, the reflection coefficient is negative. Now the B part. For a transmission line to be terminated with a pure reactance, a pure reactance does not absorb any power at all. That means the load impedance is 0, as if the load is short-circuited. Therefore, the absolute value of the reflected coefficient is 1. However, this gives the standing wave ratio to be infinity. So the C part of the question says, what is impedance matching? Impedance matching is the process whereby the input and the output impedance of an electrical load in a transmission line is decided in such a way that the signal reflection is minimized, or for the signal power now transferred to the load is maximized. To achieve this impedance matching, the following conditions are to be met. Now, the resistance of the load should be equal to that of the source. That is number one condition. That is, load resistance must be equal to the source resistance. Number two, the reactance of the load should be equal to that of the source, but opposite in sign. So it could be the inductive reactance must be equal to the capacitive reactance in an opposite sign. Which means if the source is inductive, the loads should be capacitive and vice versa. Question 8. The A aspect says, indicate the power flow patterns in a directional coupler, and B part, what are the parameters used to define an ideal directional coupler? Question 8C. Why the S parameters are used in microwaves? The A aspect, for us to indicate the power flow pattern in a directional coupler, as we have seen in the previous question, where we have the main waveguide and the auxiliary waveguide. That is, we have port 1 to be the incident power. At port 2, we have the received power. At port 3, we have the back power. And at port 4, we have the forward power. So, but under normal circumstances, the output of port 3 should be 0. Although there are some traces of a small amount of power called back power, which is practically detected at port 3. So the B part, the parameters used to define the directional coupler are, number 1, coupling factor. The coupling factor of a directional coupler is the ratio of the incident power to the forward power measured in dB, and is given to be C equals to 10 log P incident, that is P subscript I all over P subscript F, which is the forward power, in base 10 logarithms measured in dB. So number 2, directivity. The directivity of a directional coupler is the ratio of forward power to the back power measured in dB, and is given to be D equals to 10 log P forward all over P backward in base 10 logarithms measured in dB. Number 3, isolation. It defines the directive properties of a directional coupler, which is the ratio of incident power to that of back power measured in dB. That means isolation now is 10 log P incident all over P backward power into base 10 logarithms. Therefore, isolation in dB is equal to coupling factor plus the directivity. Now, in the C part of the question, why S parameters is used in microwave networks. The hybrid parameters, the admittance parameters and the impedance parameters together with the ABCD parameters are difficult at microwave frequencies due to the following reasons. Number 1, the equipment is not readily available to measure total voltage and the total current at the points of the networks. And number 2, short circuit and open circuits are difficult to achieve over a wide range of frequencies. And number 3, the presence of the active devices makes the circuit unstable for short or open circuits. Therefore, microwave circuits are analyzed using scattering or S parameters, which linearly relates the reflected wave amplitude with those of the incident waves. Question 9. What are the applications of reflex klystron? And the B part, apart from reflex klystron, what other devices are used as microwave signal sources? The C, 9C says, what is Gunn effect? And 9D, what is negative resistance in Gunn diode? Solution to A, the application of reflex klystron. Reflex klystrons are used as, number 1, signal source in microwave generators. Number 2, local oscillators in microwave receivers. Number 3, pump oscillators in parametric amplifiers. Number 4, frequency modulated oscillators in portable microwave links. Now, the B part of the question says, apart from reflex klystron, other devices used as microwave signal sources are, number 1, magnetron oscillator. Number 2, backward wave oscillator. Number 3, Gunn oscillator. Number 4, impact diode oscillator. 5, trapper diode oscillator. Okay. The C part now. The C part, Gunn effect. When the voltage gradient or the electric field across an N-type semiconducting solid, for example, a slide of gallium arsenide, exceed a certain critical threshold value of electric field of about 3300 volt per centimeter. That is like 3.3 kV, kilovolts per centimeter. A negative resistance will develop. An oscillation will also occur. Now, if the slice is connected to a suitable tank circuit, that is an LC circuit, it could also be called a resonance circuit or a tuned circuit. Now, the elements that exhibit Gunn effects are, number 1, gallium arsenide, indium phosphide, cadmium telluride, indium arsenide, so like the gallium arsenide, indium phosphide, cadmium telluride, indium arsenide, all these are the metals of the transition elements. Now, the D aspect of the question says what we understand by a negative resistance. A device is said to have a negative resistance characteristics if during its operation an increase in the voltage across it leads to decrease in its current. Question 10. A aspect say the question 10. What will be the effect on the signal values of number 1 reflection coefficient, number 2 return loss, number 3 the VSWR in a microwave network when there is no reflection, and 2 full reflection. Solution. At no reflection, load impedance is always equal to the characteristics impedance. At no reflection, the reflection coefficient is always 0. At no reflection, return loss is always at infinity. And at no reflection, VSWR is equal to 1. At full reflection, the load impedance is open, which is infinity, or we can say it could be shorted. ZL is equal to 0. The reflection coefficient is 1. The return loss is 0. The VSWR is at infinity. So, as it is shown in the related equations for reflection coefficient, return loss, and the VSWR. Therefore, if ZL equals to 0 or ZL equals to infinity, that means if the line is open circuit or short circuit, reflection coefficient is always 1, return loss equals to 0, while the voltage standing wave ratio is at infinity. Question 11. A 75 ohm line is first short terminated and minimal locations are noted. Then the short is replaced by a resistive load and another minimum locations are again noted. Now, if minimal locations are not altered and the VSWR is 3, now calculate the value of the resistance load, the resistive load. Given that Z0 is 75 ohm, VSWR is 3, so how can we calculate the load impedance? As we know that VSWR is given to be 1 plus reflection coefficient all over 1 minus reflection coefficient. By substituting our values into the equation, we have 3 is equal to 1 plus reflection coefficient all over 1 minus reflection coefficient. That gives us reflection coefficient to be 0.5. Now, to calculate the resistive load, we have the reflection coefficient to be ZL minus Z0 all over ZL plus Z0. Now, Z0 is given to be 75 ohm, VSWR is given to be 3, and the reflection coefficient to be 0.5 as calculated. So by the time we substitute these values into this equation, we have our resistive load to be 225 ohm. Question 12. What is the relationship between lambda naught, lambda g, and lambda c in a waveguide? Derive it. The B part. A rectangular waveguide has dimensions A to be 5 cm and B to be 2 cm. The signal applied to waveguide is 10 GHz. Now, determine the modes that are propagating in the waveguide. The A part. We have a guided wave. Lambda G is guided wavelength. Guided wavelength is defined as the distance traveled by a wave in a waveguide in order to undergo a phase shift of 2 pi radians, which is related by lambda G equals to 2 pi over beta. The wavelength in the waveguide is different from the wavelength in a free space. Now, the guided wavelength is related to free space wavelength and cutoff wavelength by 1 all over lambda square g, lambda g square equals to 1 all over lambda naught square minus 1 over lambda c square. Since lambda g is greater than lambda naught, that is, the guided wavelength is greater than the wavelength in free space. So if we want to get to make our lambda g to be the subject of the formula now, we have lambda naught all over the square root of 1 minus the square of the fraction of lambda naught and lambda c. The above equation is true for any mode in a waveguide of any cross section. However, the cutoff wavelength occurs at the frequency where the propagation constant is 0, or the attenuation and the phase constant both equals to 0. That is, alpha equals to 0 equals to beta. Wave propagates in the waveguide when guided wavelength is greater than the free space wavelength. The B part. The mode for which the cutoff wavelength assumes a maximum value is called the dominant mode. And we can get the different mode by using this equation. Lambda, the cutoff wavelength with parameters m and n is equal to 2ab all over the square root of m squared b squared plus n squared b squared. For a TE01 mode, the cutoff wavelength will give 2b, that is dimension of b of the rectangular waveguide, times 2. And for TE10 mode, the cutoff wavelength will be 2 times the dimension of the rectangular waveguide, a, that is 2 times a. So among all, the cutoff wavelength now for mode 10 has the maximum value, since A is the larger dimension than B. Hence, TE10 mode is the dominant mode in rectangular waveguide. All wavelengths greater than lambda c are attenuated, and the ones less than lambda c are allowed to propagate inside the waveguide. That means any wavelength greater than the cutoff wavelengths are attenuated, and the ones less than the cutoff wavelengths are allowed to propagate inside the waveguide. For TM mode, we have TM11 has the lowest cutoff frequency or the lowest cutoff wavelength of all the TM modes. Therefore, The modes that are propagating in TE modes of this waveguide is the TE10, while that of TM mode is the TM11. Thank you very much for listening. Thank you.